So now we are going to discuss about some of the advanced features available in Orca for optimizations, and one of them is GOAT, the Global Geometry Optimization and Ensemble Generator. So up to now, whatever local structure we have described, they are at best local minima. What we want to do is now to try to find global minima. All the global minima finding algorithms are generally stochastic. So the Orca algorithm, the way it works is that it's start from somewhere in the potential energy surface like this point, and then first it's optimized to the local minima, then it starts pushing upwards. Pushing upwards is by generally pushing some force by some finite temperature, and then it goes into the upward hill in a random direction until a barrier is crossed, and once this barrier is crossed in any of the direction, then a new minima is found and this process is restarted with another uphill push by an optimization, and after several of these GOAT iterations uphill downhill, if no global minima has been found between the last two global iterations, then we consider that it has reached the global minima. Now, since structures are collected along the way to the global minima, we have in the end not only the global minima but also the conformational ensemble for that molecule, meaning all the conformations it can have and their relative energy, and this will be useful later to compute Boltzmann average spectra and properties. Why one need to calculate Boltzmann average spectra and properties? Remember, the quantum chemistry what we are doing is at 0 Kelvin. Now, almost all the experiment we are going to do is actually at a finite temperature. So, that means not only the global minima, but few of the local minima will be also accessible in this temperature. So, whatever the spectra you are calculating or the property you are calculating may not only come from the global minima, but a fraction of may come from the other local minima. To actually match the experiment, you sometimes need to do a Boltzmann averaging of it. So, this will be important if we really want to do it. To give you an example, if we try to find out the global minima of this conformer glycine, so in principle the GOAT can be used in with any of the quantum chemistry method, but for all practical purposes it is very difficult to perform calculation if you are not ready to use XTB. So, we are going to use XTB for this kind of calculations. So, let me go to the folder GOAT, and this is my input file. So, what it has actually the glycine geometry, you can make the glycine geometry from Avogadro, and then you just need to give XTB and GOAT, and if you run it will give you a detailed output file. I will not do the run in front of you because it may take a long time. I will just open the output file and maybe I will show you why I have not done it, because it took it 40 minutes on my laptop. So, half of my class will go into this running only. So, I did the running before, you can try it at home yourself. So, the only important thing which is important here is to give the GOAT keyword. So, just to tell you again, it's XTB the method and just you have to give GOAT. And so, if you run it, let us read the output file line by line. So, what it does is that it first do the geometry optimization. You see the cycle 1, 2, 3, 4, it will go like this. It's just done few iterations. Oh, it's yet not converged. It's 26 cycles, is still not converged. Maybe another cycle more. So, the optimization has converged after 29 cycles. So, once as we discussed that it will first converge it to the nearest local minima, and then it will start the global optimizer algorithm. So, it will first decide walkers. So, the walkers are basically which goes into the uphill direction, and by default it is have 8 walkers. So, you can run these calculations actually entirely in parallel. So, they split the workers by 2. So, it becomes total the default number of base worker is 4 and so final number of workers become 8 because each of them is split twice. And then for each push it will have 15 optimization. So, if you run like this, so you will get the first, at the 0th iteration these are your conformers, then you have global iteration 1, global iteration 2 and global iteration 3, and by the time in 2 and 3 there is no difference in the no additional global minima is found. So, that is what you are now going to print. So, this is your 0, 1, 2, 3, 4, 5, 6. Your final ensemble is written to glycine final ensemble and your lowest energy structure is written as. So, each what is generated in each of the iterations they are given. So, we can try to open the one of them to see what is there. This is the global, the final ensembles actually contain all the structures and they are arranged energy wise. So, this is the lowest energy one and all these 10 structure which is of all the 5 structure, not 10 structure, sorry, all the 5 structure which are 1, 2, 3, 4, 5. Yes, I was correct. All the 5 structure which are lowest energy conformer they are given here. And again, I should again open the output file, I believe. Oh, this is the input file. This is the output file. Yeah. And the final ensemble structure is written at glycine final ensemble dot xyz. So, if I open it with Avogadro, maybe Chemcraft will be a better option to open it. It actually has all the geometries. So, if you want to animate between the different conformers, this is how the different conformers looks like. So, this is what the lowest energy conformer is and you can save its geometry. I believe the final conformer is also written as the glycine dot xy, glycine dot global minima also. So, this is the global minima structure. So, if you just want this structure, so you can open it with Chemcraft. So, this is the global minima. And if you want the other structures also, you can see it from the other Chemcraft version. So, this is particularly helpful if you want a various kind of configurations for doing your calculations. Now, next go to the feature of the other thing, but before that just to let you know how it works properly, there is another important utility which you can use. So, this is where we considering the global minima of a single structure. Now, let us have two molecules are interacting with each other. That is a very common situation in chemistry. To react, the molecule has to come in a proper orientation. And so, the most important aspect of chemistry physics do not occur with single molecules, but when they interact with each other. Now, given any two molecule, how to put them together in a best interacting pose, and that is one the Orca-Docker can answer. Now, given in two molecule, how to put them together in a best interacting pose, we can use the Orca-Docker algorithm for doing that, and let us take the example of water dimer. So, to give the Docker, again we are going to use XTB and we will see the keywords one by one what is important. So, you have to give a percentage Docker block and you have to give the guest, and the host is already defined in your input file. So, there are two parts of the input. This part is the input file for the host. This is the geometry is already given in this case, and and the Docker whatever is the guest that you have to provide separately in the percentage Docker block. So, it is Docker guest water.xyz and the end, and water.xyz contains the geometry of the x. So, this xyz file looks little bit special because it not only has the atom number, in the second line it has the charge and multiplicity also for the guest molecule. So, it is same water molecule. So, I have so you can see the coordinate of them is same, but in place of water I could have used any other molecule. So, the guest the host can be water and the guest can be something else. So, but to first let us run the calculation and let us see how the output files actually looks like. So, let us go to the week 7, let us make a new folder. And let us keep it at Docker. And let me open this one. Let me copy paste the input file. So, this is fine. We have missed the exclamation mark. So, now we can save it as, let us say, Docker and we want to make it an orca.inp file. And now we have to create the water.xyz. I can create from this also. Just need to copy this one. So, it is 3, then 0, 1. And this we save as in the same directory water.xyz. And like the last class, we will use the MOBIX term here, and so maybe I can zoom a little bit. So, it is Orca, Docker, So, by the time our calculation runs, let us see a little bit how it actually works. So, the basic idea behind the Docker is to use a type of swarm intelligence to find local minima for where the host would be best positioned, and based on the energy and the gradient of a given potential energy surface. So, swarm intelligence algorithms were invented to try to mimic the behavior of animals such as bees or ants, and it actually fits the problem here quite well. We will show it below. So, the basic steps needed for the algorithms are, you first need to optimize host and guest. We will come into the details of the swarm intelligence algorithm, what it does. So, it creates a spatial grid around the host and then initialize a possible set of random solution, but by placing the guest and let the swarm intelligence find the local minima, collect the fraction of the best solutions found on 4 and then fully optimize them. And the structures with the lowest energy is considered as the best possible solution. So, if you want to see it, so the swarm intelligence is like the way a flock of birds actually turns a direction, or bees actually behave, is that with the initial velocity, they of course have their individual velocities and individual direction, but they also talk to each other, and depending upon that you can see that flock of birds how they change directions. So, this information by talking to each other can also help you to find what are the most suitable positions. So, suppose I want to place water surrounding this substituted biphenyl. So, what initially we will do that is that I will put the water all around, and these dots are actually the position of the water molecules and without the hydrogen. So, they are now first placed randomly, and by using the swarm intelligence, that all of the water molecules you can see they move either to the nitrogen end or to the OH end, and at the finally the water binds best to both NH2 and OH. So, all the water molecules move to its sites. That is what how the algorithm works. So, now the calculations are running. I believe it will be happen very soon. So, now what it is doing is that it is running the final optimization on each of the individual structures and find it out where it actually has the highest interaction energy. So, I believe there will be total 7 structure, 2 more. So, it took total 6 minutes, and so all the optimized structures were saved to the all opt folder, and the lowest interaction energy is actually structure 5. So, if you go to the Docker example, this actually contains the lowest energy file. So, if I open it with Chemcraft, this is the lowest energy conformer would look like. If I want to see what other conformers are there, I can of course open it with the Chemcraft. And if you want to animate, you can see how it looks like. There are various possible configurations. Maybe we can look it one by one. So, this is the lowest energy structure. This is the next best. Of course, we have to always go to the next view. I am sorry, some of the structures are coming like shadows. To centralize it. So, this is the third lowest, this is the fourth lowest. So, if I see the output again, you can see that these interaction energies are pretty similar, and you can actually get many of this kind of binding structures. So, it is generally a good idea to use this kind of algorithm, not to remain by guesswork, but if you want to understand how to molecules will come to the best possible orientation for any reactions, then it's generally a good idea to use the Docker algorithm for this purpose. And you can use it for many innovative use, like docking a drug molecule maybe to a protein, and using a QMM method, but that will come to later. As a homework problem, your problem will be to find out what are the possible orientation the GC base pair can have. We know that the Watson-Crick GC base pair is one of the common structure, but we will see that if there are any other structure possible. So, you have to make the individual structure of guanine and cytosine maybe with Avogadro, and then make one of them as guest and one of them as host, and then use the similar kind of Docker we shown for two water molecules. Remember, here the molecules are different, and then you can find out what is the lowest energy orientation and what are the other possible orientation possible other than the popular Watson-Crick model. So, this is what we wanted to discuss about the geometry optimization. So, you have seen how to do geometry optimization, how to do it faster by optimizing in a lower level of method fast, calculating Hessians, and then read those Hessians and do calculation in a higher level of method. You have read about the special tools like GOAT and Docker. We have told that to find out it's a real local minima or a transition state, the only diagnostic is the frequencies, but frequency can give you to other handle to other properties like vibrational spectroscopy, and that is what we are going next at to.